Welcome to our journey into the fascinating world of chemical bonding. Have you ever wondered how the substances around us are formed? From the water we drink to the air we breathe, everything is made up of atoms that stick together in specific ways. This process, known as chemical bonding, is the foundation of chemistry. In this video, we'll explore why atoms bond, the different types of bonds, and how these interactions shape the properties of matter. Get ready to uncover the secrets behind the connections that hold our universe together. Let's start by understanding what drives atoms to form bonds in the first place. Atoms are always seeking stability. Most atoms are not stable on their own, so they look for ways to achieve a full outer shell of electrons. This drive for stability is what causes atoms to bond with each other. By sharing, gaining, or losing electrons, atoms can reach a more stable, lower energy state. This tendency is often called the Octet Rule, which means atoms are happiest when they have 8 electrons in their outer shell. Understanding this rule helps explain why certain elements react the way they do and why chemical bonds form in the first place. Chemical bonds come in several varieties, each with unique characteristics. The three main types are ionic, covalent, and metallic bonds. Ionic bonds form when one atom donates an electron to another, creating charged ions that attract each other. Covalent bonds occur when atoms share electrons, resulting in a strong connection. Metallic bonds, on the other hand, involve a sea of shared electrons moving freely among metal atoms. Each type of bond leads to different properties in the materials they form, from the hardness of salt to the flexibility of metals. Let's dive deeper into ionic bonds. These bonds usually form between metals and nonmetals. For example, sodium, a metal, can give up an electron to chlorine, a nonmetal, resulting in positively charged sodium ions and negatively charged chloride ions. The opposite charges attract, holding the ions together in a crystal lattice. This is how table salt or sodium chloride is formed. Ionic compounds tend to have high melting points and conduct electricity when dissolved in water, thanks to the movement of ions. Covalent bonds are all about sharing. When two nonmetal atoms come together, they can share pairs of electrons to achieve stability. This sharing creates a strong bond between the atoms. Water is a classic example. Each hydrogen atom shares an electron with oxygen, forming a stable molecule. Covalent compounds can exist as gases, liquids, or solids, and they often have lower melting points compared to ionic compounds. These bonds are essential for building the complex molecules that make up living things. Metallic bonds are unique to metals. In this type of bond, atoms release some of their electrons, which then move freely throughout the entire structure. This sea of electrons allows metals to conduct electricity and heat efficiently. It also gives metals their characteristic properties like malleability and ductility, meaning they can be shaped and stretched without breaking. The strength and flexibility of metallic bonds are why metals are used in construction, electronics, and countless other applications. Octet rule plays a central role in chemical bonding. Most atoms strive to have 8 electrons in their outermost shell, which is considered a stable configuration. This rule explains why atoms gain, lose, or share electrons during bonding. While there are exceptions, especially among transition metals and some lighter elements, the Octet rule is a helpful guideline for predicting how atoms will interact. Understanding this rule makes it easier to grasp why certain compounds form and why others do not. Electronegativity is a measure of how strongly an atom attracts electrons in a bond. Some atoms, like fluorine, are highly electronegative and pull electrons closer to themselves. Others, like sodium, have low electronegativity and tend to lose electrons. The difference in electronegativity between atoms helps determine the type of bond that forms, whether it's ionic, covalent, or somewhere in between. This concept is key to understanding the behavior of molecules and their chemical reactions. Not all covalent bonds are created equal. When two atoms share electrons unequally, the bond is called polar covalent. This happens when one atom is more electronegative than the other, pulling the shared electrons closer. Water is a classic example, with oxygen pulling electrons away from hydrogen. In nonpolar covalent bonds, the electrons are shared equally, as seen in molecules like nitrogen gas. The polarity of a bond affects the properties of the molecule, including how it interacts with other substances. Atoms gain or lose electrons. They become ions, charged particles that play a crucial role in chemistry. Positive ions are called cations, while negative ions are anions. Ionic compounds are formed when these oppositely charged ions attract each other and arrange themselves in a repeating pattern, known as a crystal lattice. This structure gives ionic compounds their characteristic hardness and high melting points. Understanding ions is key to grasping how ionic bonds work. Molecules are groups of atoms held together by covalent bonds. When two or more different elements combine covalently, they form molecular compounds. These compounds can have a wide range of properties, from the gases we breathe to the liquids we drink. The arrangement and type of atoms in a molecule determine its shape, reactivity, and physical characteristics. Molecular compounds are essential in biology, medicine, and industry, making them a vital part of our daily lives. Let's take a closer look at metallic bonding. In metals, the outer electrons are not tied to any one atom. Instead, they move freely throughout the entire structure, creating a flexible and conductive material. This is why metals can be hammered into sheets or drawn into wires without breaking. The free movement of electrons also explains why metals are shiny and good conductors of electricity and heat. Metallic bonding is what gives metals their unique set of properties. Lewis dot structures are a simple way to represent the valence electrons in atoms and molecules. By drawing dots around the chemical symbol, we can visualize how atoms share or transfer electrons during bonding. These diagrams help predict the arrangement of atoms in a molecule and the type of bonds that will form. Learning to draw Lewis structures is a valuable skill for anyone studying chemistry, as it makes complex concepts much easier to understand. Bond energy refers to the amount of energy required to break a bond between two atoms. The higher the bond energy, the stronger and more stable the bond. This concept helps explain why some molecules are more reactive than others. For example, the bonds in nitrogen gas are very strong, making it relatively unreactive. Understanding bond energy is crucial for predicting chemical reactions and the stability of compounds. Bond length is the distance between the nuclei of two bonded atoms. Generally, shorter bonds are stronger because the atoms are held more tightly together. Single bonds are longer and weaker than double or triple bonds, which pull the atoms closer. The relationship between bond length and strength is important for understanding molecular structure and reactivity. Chemists use this information to predict how molecules will behave in different environments. Valence electrons are the outermost electrons of an atom and play a key role in chemical bonding. These electrons are involved in forming bonds with other atoms, either by being shared, gained, or lost. The number of valence electrons determines an element's chemical properties and its place in the periodic table. Elements in the same group have similar valence electron configurations, which is why they often react in similar ways. Periodic table is a powerful tool for predicting chemical bonding. Elements are arranged according to their atomic number and electron configuration, which reveals patterns in their bonding behavior. For example, elements in the same column often form similar types of bonds. The table also helps us understand trends like electronegativity and atomic size, both of which influence how atoms interact. Mastering the periodic table is essential for anyone studying chemistry. Atoms can form single, double, or triple bonds depending on how many pairs of electrons they share. A single bond involves one pair of shared electrons, a double bond has two pairs, and a triple bond has three. Each type of bond has different strengths and lengths, with triple bonds being the shortest and strongest. The type of bond affects the molecule's stability and reactivity, influencing how it behaves in chemical reaction. Nonpolarity arises when atoms in a bond have different electronegativities, causing electrons to be shared unequally. This creates a dipole, with one end of the bond slightly negative and the other slightly positive. Dipoles influence how molecules interact with each other, affecting properties like solubility and boiling point. Understanding bond polarity is key to predicting the behavior of molecules in different environments. Beyond the bonds within molecules, there are forces that act between molecules known as intermolecular forces. These include hydrogen bonds, dipole-dipole interactions, and London dispersion forces. Intermolecular forces are weaker than chemical bonds but play a crucial role in determining the physical properties of substances, such as boiling and melting points. They explain why water is liquid at room temperature and why oil and water don't mix. Hydrogen bonding is a special type of intermolecular force that occurs when hydrogen is bonded to highly electronegative atoms like oxygen, nitrogen, or fluorine. These bonds are much stronger than other intermolecular forces and are responsible for many unique properties of water, such as its high boiling point and surface tension. Hydrogen bonds are also vital in biology, holding together the two strands of DNA. London dispersion forces are the weakest type of intermolecular force, but they are present in all molecules. These forces arise from temporary fluctuations in electron distribution, creating momentary dipoles that attract neighboring molecules. While weak, London dispersion forces become significant in large molecules and contribute to the properties of substances like waxes and oils. They help explain why some nonpolar substances can still condense into liquids or solids. Dipole-dipole interactions occur between molecules that have permanent dipoles, meaning they have regions of partial positive and negative charge. These interactions are stronger than London dispersion forces, but weaker than hydrogen bonds. Dipole-dipole forces influence the boiling and melting points of polar compounds and play a role in how substances dissolve in each other. Recognizing these interactions helps explain many everyday phenomena. Shape of a molecule is determined by the arrangement of its atoms and the angles between its bonds. These bond angles are influenced by the number of electron pairs around the central atom, both bonding and non-bonding. The shape of a molecule affects its physical and chemical properties, including reactivity and how it interacts with other molecules. Understanding molecular geometry is key to predicting the behavior of substances. Valence shell electron pair repulsion, VSEPR theory is used to predict the shapes of molecules. According to VSEPR, electron pairs around a central atom repel each other and arrange themselves as far apart as possible. This determines the geometry of the molecule, such as linear, bent, or tetrahedral shapes. VSEPR theory is a powerful tool for visualizing and understanding molecular structure. The molecules can't be represented by a single Lewis structure. Instead, they have resonance structures, which are multiple valid ways to arrange electrons. The true structure is a hybrid of these possibilities, leading to greater stability. Resonance is common in molecules like ozone and the nitrate ion. Recognizing resonance helps explain the properties and reactivity of many important compounds. Coordinate covalent bond forms when one atom provides both electrons for a shared pair in a covalent bond. This type of bond is found in many complex ions and molecules, such as the ammonium ion. While similar to regular covalent bonds, coordinate bonds are important in understanding the structure and reactivity of certain compounds, especially in coordination chemistry. Hybridization is a concept that explains how atomic orbitals mix to form new equivalent orbitals for bonding. For example, in methane, carbon's orbitals hybridize to form 4 identical bonds with hydrogen. Hybridization helps explain the shapes and bond angles of molecules, making it a key idea in modern chemistry. Understanding hybridization allows chemists to predict molecular structure and reactivity more accurately. Covalent bonds can be classified as sigma or pi bonds. Sigma bonds are formed by the direct overlap of orbitals and are the strongest type of covalent bond. Pi bonds result from the side-by-side overlap of orbitals and are found in double and triple bonds. The combination of sigma and pi bonds determines the strength and properties of multiple bonds in molecules. Recognizing these bonds is essential for understanding molecular structure. Dissociation energy is the energy required to break a specific bond in a molecule. This value varies depending on the atoms involved and the type of bond. High bond dissociation energy means the bond is strong and the molecule is stable. This concept is important for understanding chemical reactions, as breaking and forming bonds involves energy changes that drive the process. Ionic and covalent compounds have distinct properties due to the nature of their bonds. Ionic compounds like table salt are usually solid, have high melting points, and conduct electricity when dissolved in water. Covalent compounds such as sugar can be gases, liquids, or solids and often have lower melting points. Understanding these differences helps us predict how substances will behave in different situations. Type of chemical bond influences a substance's solubility. Ionic compounds tend to dissolve well in water because water molecules can surround and separate the ions. Covalent compounds may or may not dissolve depending on their polarity. Nonpolar covalent compounds like oil do not mix with water. Understanding solubility is important in fields ranging from medicine to environmental science. Ability of a substance to conduct electricity depends on its bonding. Ionic compounds conduct electricity when melted or dissolved, as ions are free to move. Metals conduct electricity in solid form due to their sea of electrons. Most covalent compounds do not conduct electricity, except for some special cases like acids in water. Knowing the bond type helps predict a material's electrical properties. Chemical bonding is at the heart of biology. The structure and function of proteins, DNA, and other biomolecules depend on covalent, ionic, and hydrogen bonds. These bonds determine how molecules fold, interact, and carry out life processes. Understanding bonding in biological molecules is essential for fields like genetics, medicine, and biotechnology. From plastics to metals to ceramics, the properties of everyday materials are determined by the types of bonds holding their atoms together. Plastics are made of long chains of covalently bonded molecules, while ceramics often have ionic and covalent bonds. Metals rely on metallic bonding for their strength and flexibility. Recognizing the role of bonding helps us understand why materials behave the way they do. Chemical reactions involve breaking old bonds and forming new ones. The energy required to break bonds and the energy released when new bonds form determine whether a reaction is endothermic or exothermic. Understanding bonding is key to predicting reaction outcomes, rates, and the energy changes involved. This knowledge is fundamental to chemistry and many practical applications. Crystals are solids with atoms arranged in a repeating pattern. The type of bonding, ionic, covalent, or metallic, determines the crystal's properties. Ionic crystals like salt are hard and brittle. Covalent crystals such as diamond are extremely hard. Metallic crystals are malleable and conductive. The study of crystal bonding is important in materials science and engineering. Color of many substances is influenced by the way their atoms are bonded. Transition metals, for example, can form colorful compounds due to the movement of electrons between energy levels. The type of bond and the arrangement of atoms affect how a substance absorbs and reflects light. This principle is used in dyes, pigments, and even in understanding the colors of gemstones. Some materials are magnetic because of the way their atoms are bonded and arranged. In metals like iron, the alignment of electrons in certain bonds creates magnetic fields. The study of bonding and magnetism is important in developing new technologies, from electric motors to data storage devices. Understanding the link between bonding and magnetism opens up exciting possibilities in science and engineering. Conductors are materials that allow electricity to flow easily, thanks to their bonding. Metals are excellent conductors because their electrons are free to move throughout the structure. This property is essential for electrical wiring, electronics, and many other applications. The study of bonding in conductors helps us design better materials for technology and industry. Insulators are materials that do not conduct electricity well. Their atoms are bonded in such a way that electrons are tightly held and cannot move freely. Examples include rubber, glass, and most plastics. Understanding the bonding in insulators is important for safety and efficiency in electrical systems, as these materials prevent unwanted flow of electricity. Semiconductors have bonding characteristics between those of conductors and insulators. Their ability to conduct electricity can be controlled by adding impurities or changing temperature. Silicon, a common semiconductor, is the backbone of modern electronics. The study of bonding in semiconductors is crucial for developing computers, smartphones, and solar cells. Nanotechnology relies on controlling chemical bonds at the atomic and molecular level. By designing materials with specific bonding patterns, scientists can create new substances with unique properties. This field is revolutionizing medicine, electronics, and materials science. Understanding chemical bonding is the key to unlocking the potential of nanotechnology. Chemical bonding plays a vital role in environmental chemistry. The way pollutants interact with air, water, and soil depends on their bonding. Understanding these interactions helps scientists develop methods to clean up pollution and protect the environment. From greenhouse gases to water treatment, chemical bonding is at the heart of many environmental solutions. We've explored the world of chemical bonding, from the basics of why atoms bond to the complex interactions that shape our world. Understanding chemical bonds helps us explain the properties of materials, predict chemical reactions, and develop new technologies. Whether in biology, industry, or the environment, chemical bonding is a fundamental concept that connects all of chemistry. Keep exploring, and you'll discover even more about the amazing world of atoms and molecules.